Okay, now we're going to talk about the differential form of Gauss's law. So in the examples before, we have always used a constant field at any point on the Gaussian surface. That meant we could take E out of the integration because it was the same at all points on the surface we were integrating over. Now we're going to look at the case when the electric field is not constant over the Gaussian surface. So if we have the electric field at point A as E, then the electric field at point B is going to be that at A plus any change in the field that happened in that distance. Now, we haven't moved in Y or Z at all, so those components are not affected, and that means we can use a partial derivative. Remember, a partial derivative is just a derivative that treats the other components as if they were a constant. So the electric field at point B will be the electric field at point A plus any difference in the electric field that happened between point A and point B. So we can also write this as the partial differential of E in the x direction, so the rate of change of E in the x direction times the distance that we've gone in the x direction. So that's the electric field at point B. So now if you want to know the net flux between the two end surfaces, which is just the difference in the flux between the two end surfaces, you have to integrate in both of these directions as well. So basically we can multiply, so we've got the electric field, we can multiply that by the area to get to the flux. So here we have the field at point B times the area of the square on the end at point B, then the field at point A and the area times the area of the block at point A, and they cancel out a bit to give this. Then if we do the same thing for the other two pairs of surfaces and add them all together, we will get this. So this is an expression for the net flux that is going through this little chunk of volume up there. Now we can equate that to the right hand side of Gauss's law, and the charge contained is equal to the charge density times the volume. If we now cancel the dx, dy, dz's, or more properly integrate both sides, then we get this. Grad.E is the divergence V, which is the flux per unit volume, because we had the net flux on this line here and we divided by the volume, and that gave us the divergence of E. So it's the flux per unit volume. Now, what does divergence mean in terms of electric field? Well, if you have denser field lines coming out of the surface at B than we had going into the surface at A, then overall you are gaining flux within that volume, and the volume must contain some positive charge, so it's acting as a source of flux, and we say that the divergence is positive. If we have more flux lines going in at A and less coming out at B, then the volume is acting as a sink of flux, and the divergence is negative. Or you could say we've got convergence. If we have exactly the same number of flux lines going in at surface A as we have coming out at surface B, then there is no net flux and the divergence is zero.